There's something unsettling about looking up at the night sky and realizing it's hiding a secret one so vast it defies everything we thought we knew about the universe. Picture this: galaxies, those colossal islands of stars and dust, aren't just drifting aimlessly through space. They're being pulled, as if by some unseen hand, toward a point beyond the edge of everything we can observe. This isn't science fiction. It's called dark flow, and it's one of the most baffling mysteries in modern cosmology. Why are galaxies moving towards something we can't see? What could possibly exert such a gravitational grip on the fabric of the cosmos itself? The answers, or rather, the lack of them, force us to confront how little we truly understand about the universe we call home. Think about the scale of this mystery for a moment. We're not talking about a single star or even a cluster of galaxies behaving oddly. This is a coordinated motion, a cosmic river of galaxies all streaming in the same direction, as if something immense, something beyond our observable universe, is tugging at them. Scientists first noticed this strange phenomenon while studying the cosmic microwave background, the faint afterglow of the Big Bang. The data revealed something impossible: patches of the universe moving faster than they should, as if influenced by a force that shouldn't exist. The implications are staggering. If dark flow is real, it means there's something out there, something so enormous it warps the very structure of space-time on a scale we can't even comprehend. So what could it be? Another universe lurking just beyond the edge of our own. A colossal structure, so vast it makes superclusters look tiny by comparison. Or perhaps it's a flaw in our understanding of gravity itself, a crack in the foundation of physics that hints at deeper, undiscovered laws. Whatever the truth, dark flow challenges us to rethink the boundaries of reality. It's a reminder that the universe is far stranger, far more mysterious than we ever imagined. And that's what makes this journey so thrilling. Because when the cosmos throws us a puzzle this profound, it's not just about finding answers, it's about rediscovering our place in the grand, unfathomable tapestry of existence. So let's dive in, because the story of dark flow isn't just about galaxies moving where they shouldn't. It's about the limits of human knowledge and the breathtaking possibility that we're on the verge of uncovering something truly extraordinary. In 2008, something extraordinary disrupted the quiet calculations of astronomers. While mapping the movement of galaxy clusters, some of the largest structures in the universe, they noticed a pattern that shouldn't exist. These immense cosmic gatherings weren't just expanding outward as the Big Bang theory predicted. Instead, hundreds of them were racing toward the same distant region of space, like leaves caught in an invisible current. The speeds were staggering, some clusters moving at over 2 million miles per hour, far faster than the known forces of the universe could explain. It was as if a cosmic magnet, hidden beyond the horizon of our observable universe, was pulling them toward something we couldn't see. The team behind this discovery used data from the Wilkinson Microwave Anisotropy Probe, a satellite designed to study the faint glow of the early universe. By analyzing subtle distortions in this ancient light, they could trace the motion of galaxy clusters across billions of light years. What they found defied expectations. The clusters weren't just drifting randomly, they were streaming in unison toward a patch of sky near the constellations Centaurus and Vela. Scientists called this eerie phenomenon dark flow, a nod to the mysterious dark matter and dark energy that already puzzle cosmologists. But unlike those invisible forces, dark flow suggested something even more unsettling, an influence from outside our known universe. Imagine standing in a vast, foggy field, able to see only a few feet in any direction. Suddenly, you notice everything around you: the grass, the leaves, even the fog itself, leaning toward one unseen point beyond the mist. That's the essence of dark flow. The observable universe is our foggy field, and whatever lies beyond it is pulling at the fabric of reality itself. Some theories suggest it could be the gravitational tug of another universe, a colossal sibling to our own in the multiverse. Others propose a remnant of the chaotic conditions before the Big Bang, a scar in space-time still influencing the cosmos. What makes dark flow so revolutionary isn't just the mystery of its origin, it's the way it challenges the bedrock principles of cosmology. For decades, scientists believed the universe was uniform on the largest scales, with matter evenly distributed and expansion smooth and predictable. Dark flow throws that assumption into question. If galaxies are being pulled off course, it means there's structure beyond structure, forces acting on scales so vast they dwarf even the cosmic web we've spent centuries mapping. It's a humbling reminder that for all our telescopes and equations, the universe still holds secrets we've only begun to glimpse. And here's the most tantalizing part: dark flow isn't just a relic of the past. It's happening right now, a silent river of galaxies rushing toward the unknown. Every second, millions of stars are being drawn toward something we can't see, can't measure, and barely understand. That's the thrill of cosmology. The moment you think you've grasped the rules, the universe reveals a new puzzle, one that might rewrite everything we thought we knew. Dark flow isn't just another cosmic oddity, it's a phenomenon that rewrites the rules of how we understand the universe's behavior. To grasp why this discovery is so revolutionary, let's break it down. Imagine the universe as a vast ocean with galaxies like ships drifting on its surface. According to the Big Bang theory, those ships should be moving apart in a predictable, uniform way as the ocean expands. But dark flow reveals something startling. Entire fleets of galaxies are veering off course, drawn toward some distant, unseen shore. This isn't just a slight deviation. These galaxy clusters are moving with such coordinated precision that it suggests an immense gravitational presence, one so powerful it defies everything we know about the distribution of matter in the cosmos. What sets dark flow apart from other cosmic mysteries like dark matter or dark energy is its origin. Dark matter binds galaxies together, while dark energy drives the universe's accelerating expansion. Both operate within the observable universe. Dark flow, on the other hand, points to something outside it, a force acting from beyond the edge of what we can see. Think of it like sitting in a boat and feeling a current tug you toward a waterfall just beyond the horizon. You can't see the waterfall, but the water's movement tells you it's there. That's the essence of dark flow. The universe is whispering to us about something monumental lurking in the unseen dark. The implications are staggering. If dark flow is real, it challenges the cosmological principle, a foundational idea that the universe is roughly the same in all directions on large scales. Instead, it hints at a cosmos far more uneven and dynamic than we ever imagined. Some theorists propose that dark flow could be evidence of a neighboring universe in the multiverse, exerting gravitational influence on our own. Others speculate it might trace back to irregularities in the fabric of space-time from before the Big Bang, like cosmic scars that never fully healed. But here's the catch: not all scientists agree dark flow exists. Skeptics argue that the data could be distorted by measurement errors or local phenomena mimicking a larger pattern. After all, studying the motion of galaxy clusters across billions of light-years is like trying to map the path of a single dust mote in a hurricane. Yet even the possibility of dark flow has ignited fierce debate and inspired new missions like the European Space Agency's Euclid telescope, designed to probe these mysteries with unprecedented precision. Whether dark flow is confirmed or debunked, its very proposal has already reshaped cosmology. It's a reminder that the universe is under no obligation to make sense to us, and that the most profound discoveries often begin with a single, inconvenient anomaly. Every galaxy caught in this mysterious current is a clue, a breadcrumb leading us toward answers that might redefine reality itself. And that's what makes science so exhilarating. The moment we think we've mapped the edges of the known, the cosmos reveals a new frontier, vast and uncharted. One of the most fascinating contradictions in modern cosmology is the tug-of-war between two cosmic forces, the relentless expansion of the universe and the mysterious pull of dark flow. On one hand, we've known for decades that space itself is stretching, carrying galaxies away from each other like dots on an inflating balloon. This expansion is driven by dark energy, an invisible force that seems to be accelerating the universe's growth. But dark flow throws a wrench into this tidy picture. Instead of drifting apart, hundreds of galaxy clusters are moving in unison toward a single patch of the cosmos, as if some unseen hand is guiding them. It's like watching a river flow upstream. Everything we thought we knew about gravity and cosmic motion says this shouldn't be possible. The conflict between these two phenomena forces scientists to confront a critical question. Is dark flow revealing a gap in our understanding of the universe's expansion, or is it evidence of something even more extraordinary? One camp argues that the observations might stem from imperfections in our measurements or local gravitational effects we haven't fully accounted for. After all, mapping the motion of galaxies across billions of light years is an unimaginably complex task, and even tiny errors could create the illusion of a larger pattern. But if the data holds up, the implications are profound. Dark flow suggests that the universe isn't just expanding uniformly, it's being tugged in a specific direction by something beyond our observational limits. This is where things get truly mind-bending. Some theorists propose that dark flow could be the gravitational fingerprint of another universe, one that exists parallel to our own. In this scenario, the multiverse isn't just a speculative idea, it's a tangible force pulling on our galaxies like a cosmic neighbor leaning over the fence. Others suggest that dark flow might trace back to the earliest moments of the Big Bang, when the fabric of space-time was still uneven, leaving behind ripples that continue to steer matter in unexpected ways. Imagine blowing up a balloon with a slight dent even as it expands. That irregularity would shape how everything inside moves. The debate over dark flow isn't just academic, it's a battle for the soul of cosmology itself. If confirmed, it would mean that our universe isn't the isolated, self-contained system we once thought. There could be structures so vast they span multiple universes, or gravitational echoes from a time before time. And even if dark flow is eventually explained by more mundane causes, its very existence as a puzzle reminds us how much we still have to learn. Every anomaly, every contradiction is a signpost pointing toward deeper truths. So while the universe expands, dark flow pulls us in the opposite direction, not just toward a patch of distant sky, but toward a future where the cosmos might surprise us all over again. Long before dark flow entered the cosmic conversation, astronomers were already grappling with another gravitational enigma, the Great Attractor. Picture our galactic neighborhood, with the Milky Way and thousands of nearby galaxies all being drawn toward a single point in space like moths to a flame. This mysterious region, located about 250 million light-years away in the direction of the constellation Centaurus, exerts such a powerful pull that it warps the motion of everything around it. For decades, the Great Attractor remained hidden behind the dense plane of our own galaxy, its secrets obscured by cosmic dust. even today, with advanced telescopes piercing through that veil, we've only uncovered part of the story. The Great Attractor isn't just a lone anomaly. It's part of an even larger structure called the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years. But here's where things get even stranger. Dark flow takes this mystery and cranks it up to an unimaginable scale. While the Great Attractor influences galaxies relatively close to us, dark flow involves clusters thousands of times farther away, all moving in sync toward something beyond the observable universe. It's as if the Great Attractor were just a small whirlpool in a river, while dark flow reveals the entire river is being pulled toward a colossal waterfall we can't even see. This raises a tantalizing question. Could these two phenomena be connected? Some scientists speculate that the Great Attractor might be a local expression of a much grander gravitational tide, one that stretches across the cosmos, all the way to whatever lurks in the unseen dark. Yet the numbers don't quite add up. The Great Attractor's pull, while immense, simply isn't strong enough to explain the staggering speeds of dark flow. This discrepancy hints at something even more extraordinary. Imagine standing on a beach, feeling the tug of a nearby tide pool, only to realize the entire ocean is being drawn toward a distant, moonless horizon. That's the scale we're dealing with. If dark flow is real, it suggests the existence of structures or forces so vast they make superclusters like Laniakea look like specks of dust. Theories abound. Perhaps the Great Attractor is just one node in a cosmic filament, a thread in a tapestry so enormous it extends beyond our observational limits. Or maybe dark flow is evidence of a primordial unevenness in the universe, a relic from the first moments after the Big Bang, when space-time itself was still settling into its shape. There's even a radical idea that dark flow and the Great Attractor might be shadows cast by a higher dimensional structure, a wrinkle in reality that our three-dimensional minds can't fully visualize. What's clear is this: the universe loves to humble us. Just when we think we've mapped the limits of the known, it reveals another layer, another mystery waiting to be unraveled. The Great Attractor was once the frontier of our ignorance. Now, dark flow has pushed that frontier even farther out into the uncharted dark. And that's the beauty of cosmology. Every answer leads to a deeper question. Every discovery opens a door to something even more profound. Detecting dark flow is like trying to hear a whisper in a hurricane. It demands instruments so precise they can measure the universe's faintest echoes. Scientists rely on the cosmic microwave background, the afterglow of the Big Bang, as their ultimate reference point. This ancient light, which has traveled for over 13 billion years, carries subtle clues about the motion of everything in the cosmos. But here's the catch: galaxies don't just move through space, they leave fingerprints on this primordial radiation as they go. When a galaxy cluster barrels through the cosmic microwave background, its hot gas distorts the light in a telltale way, a phenomenon called the kinematic Sunyaev-Zel'dovich effect. It's like watching ripples in a pond bend around a speeding boat. The pattern of distortion reveals both the direction and speed of the cluster's motion. These distortions are incredibly faint, requiring telescopes with unparalleled sensitivity. Instruments like the Planck satellite and the Atacama Cosmology telescope have spent years mapping these minute variations, piecing together a cosmic motion picture frame by frame. The data is meticulous, painstaking. A single misstep could turn a groundbreaking discovery into a statistical fluke. Imagine trying to track the drift of a cloud by studying how it scatters sunlight, but from thousands of miles away with a camera that sees only the faintest shadows. That's the scale of precision needed to detect dark flow. Yet even with these technological marvels, controversy lingers. Some researchers argue that what looks like dark flow could be the result of local gravitational tugs or systematic errors in the data. After all, the cosmic microwave background itself isn't perfectly uniform. It's dotted with warmer and cooler patches, remnants of the universe's infancy. Disentangling these natural fluctuations from the signal of moving galaxy clusters is like trying to pick out a single voice in a choir. But the teams behind these studies have run the numbers repeatedly, accounting for every conceivable source of noise. The signal persists stubborn and unexplained. What makes this detective work so revolutionary isn't just the technical achievement, it's the audacity of the claim. Dark flow suggests that our universe isn't the isolated bubble we once thought. If galaxy clusters are truly being pulled by something beyond the cosmic horizon, it implies a reality far grander than we've dared to imagine. Every measurement, every pixel of distorted light is a vote in a cosmic referendum. Are we alone in the cosmos, or is there something or someone else out there shaping the universe in ways we're only beginning to see? The answers won't come easily, but in the hunt for dark flow, even the uncertainties are exhilarating, because when the universe gives you a mystery this profound, the search for truth becomes its own reward. The cosmological principle has been a cornerstone of modern astronomy, the quiet assumption that on the grandest scales, the universe is smooth and uniform no matter where you look. It's why we can point telescopes in any direction and expect to see roughly the same distribution of galaxies, the same cosmic web stretching toward infinity. But dark flow throws a wrench into this elegant symmetry. If hundreds of galaxy clusters are all streaming toward some unseen horizon, it suggests the universe isn't just uneven, it's lopsided, tugged out of shape by forces beyond our current understanding. Picture a perfectly balanced scale, meticulously calibrated to hold equal weights on both sides. Now imagine someone placing an invisible hand on one side, tipping it ever so slightly. That's what dark flow does to our models of the cosmos. The imbalance isn't just a minor discrepancy, it's a fundamental challenge to how we've mapped reality itself. For decades, the cosmological principle guided everything from the Big Bang theory to our understanding of dark energy. It was the glue holding the universe's story together. But if dark flow is real, that glue might be coming undone. Critics argue that the signal could be an illusion, a quirk of how we measure distant motions. After all, the universe is full of gravitational wrinkles, superclusters, voids, and filaments that tug matter in unpredictable ways. Could dark flow just be the accumulated pull of countless unseen structures, like a cosmic game of telephone where each whisper distorts the message? Maybe, but the scale of the motion defies easy explanation. We're not talking about a few galaxies swaying off course. This is a coordinated march, a cosmic migration spanning billions of light years, all pointing toward something outside the playbook. The implications ripple far beyond astronomy textbooks. If the cosmological principle cracks, it forces us to rethink some of the universe's most basic rules. Could the Big Bang have left behind uneven scars, regions of space-time forever tilted by the violence of creation? Or is dark flow a hint that our universe isn't the only one, that we're floating in a vast multiverse, nudged by the gravity of invisible neighbors? Either way, the stakes couldn't be higher. This isn't just about galaxies moving where they shouldn't. It's about whether we've been reading the cosmos all wrong, mistaking a single page for the entire story. And that's the thrill of science at its best. Every paradigm shift begins with an anomaly, a stubborn fact that refuses to fit. Dark flow might be that anomaly, a cosmic whisper urging us to look beyond the edges of our maps. Because if the universe isn't as uniform as we thought, who knows what else is waiting in the dark? If dark flow is real, it doesn't just hint at unseen forces. It opens the door to realities beyond our wildest imagination. One of the most tantalizing theories suggests that what we're witnessing is the gravitational fingerprint of another universe, a cosmic neighbor in the multiverse. Picture two soap bubbles floating close together, their surfaces nearly touching. Even if they never collide, the gravity from one could subtly distort the shape of the other. If our universe is one of those bubbles, dark flow might be the gentle tug of another bubble just beyond our observational horizon. This isn't just speculation. Some models of string theory and quantum cosmology actually predict such a scenario where universes exist in vast, interconnected webs, each with its own laws of physics. The idea that we're feeling the pull of another reality is both exhilarating and humbling, a reminder of how small our corner of existence might truly be. But not all scientists are ready to leap into the multiverse. Another camp argues that dark flow could be an echo from the universe's violent birth, a relic of the chaotic conditions that existed in the first fractions of a second after the Big Bang. Imagine stretching a rubber sheet and then releasing it even after it settles. Tiny wrinkles remain. If space-time itself was stretched unevenly in those primordial moments, those wrinkles could still be guiding the motion of galaxies today, creating the illusion of a mysterious pull. This theory doesn't require any unseen universes, just a deeper understanding of our own cosmic infancy. Then there's the possibility that dark flow isn't a cosmic anomaly at all. It might be a flaw in how we interpret the data. Mapping the universe is like reconstructing a puzzle with missing pieces, and sometimes the gaps can trick us into seeing patterns that aren't there. Could local gravitational effects, measurement errors, or even the way light bends around massive structures be masquerading as a coordinated flow? It's a sobering counterpoint, one that reminds us how easy it is to mistake noise for signal when peering into the abyss. What's remarkable about these competing theories isn't just their differences, it's how each one, if proven true, would rewrite the rules of physics. The multiverse idea challenges our understanding of reality itself, suggesting we're part of something far grander. The primordial wrinkle theory pushes us to reconsider the Big Bang's aftermath, while the data flaw argument forces us to refine our tools and methods. In a way, dark flow is less about the answer and more about the questions it forces us to ask. Because whether it's evidence of parallel worlds, cosmic scars, or simply human error, one thing is certain: the universe still has secrets it's not ready to give up. And that's what makes this mystery so irresistible. Every conflicting theory, every heated debate is a testament to the fact that we're still explorers, charting the edges of the unknown. Dark matter and dark energy are the invisible architects of our universe, shaping its structure and destiny in ways we're still unraveling. Dark matter acts like cosmic glue, its gravitational pull holding galaxies and clusters together, while dark energy works in opposition, stretching space itself apart with relentless force. Together, they form the backbone of modern cosmology, yet neither can account for the eerie phenomenon of dark flow. This isn't just a gap in our knowledge, it's a chasm, suggesting the existence of a third, shadowy player in the cosmic equation, something that bends gravity to its will on scales we've never before imagined. Think of it like this: if the universe were a grand puppet show, dark matter would be the strings keeping galaxies from flying apart, and dark energy would be the stage expanding beneath them. But dark flow, that's the unseen hand yanking the entire stage toward the wings, a force so profound it overrides the usual rules of the performance. The numbers don't add up. The gravitational influence of all the dark matter we've mapped every filament of the cosmic web, every hidden halo surrounding galaxies still can't explain why galaxy clusters are racing toward the same distant point at millions of miles per hour. Dark energy, meanwhile, should be driving everything apart uniformly, not shepherding galaxies in a coordinated march. So what's missing? Some theorists propose that dark flow might be evidence of a new kind of gravitational interaction, one that operates beyond the reach of dark matter and dark energy. Picture gravity as a radio signal. We've spent centuries tuning into one frequency, the one described by Einstein's equations. But what if dark flow is static from another channel entirely, a signal from a deeper, hidden layer of physics? Others wonder if it's tied to the quantum foam of space-time itself, fluctuations so vast they ripple across the cosmos, nudging matter in ways we're only beginning to detect. Then there's the radical possibility that dark flow isn't about matter or energy at all, but about the very fabric of reality. Could the universe have a preferred direction, a cosmic North Pole imprinted at the moment of creation? It's a notion that would have made Einstein balk, yet the data forces us to consider it. Every alternative feels like grasping at shadows, but that's the nature of frontier science. Dark flow doesn't just challenge our models, it exposes how much we've taken for granted. For all our telescopes and supercomputers, the universe still holds cards it hasn't shown us. And that's what makes this more than just a puzzle. It's an invitation to rethink everything. The universe's first moments were anything but calm. In the tiniest fraction of a second after the Big Bang, space itself erupted in a violent growth spurt called cosmic inflation, expanding faster than the speed of light. This explosive stretch didn't just create the cosmos we know, it planted the seeds for everything within it, from galaxies to galaxy clusters. But what if it also left behind something even more profound? What if dark flow isn't a mysterious anomaly but an ancient echo of that primordial chaos, a cosmic fossil from the universe's infancy? Inflation theory suggests that quantum fluctuations, tiny ripples in the fabric of space-time, were stretched to enormous scales during that rapid expansion. These ripples eventually became the blueprints for the large-scale structure of the universe, the gravitational scaffolding that shaped galaxies and superclusters. But here's the twist: if those fluctuations weren't perfectly uniform, they could have created imbalances on scales far larger than our observable universe. Picture a lake freezing over. The ice doesn't form perfectly smooth. Tiny cracks and ridges emerge, creating patterns that stretch far beyond any single patch of ice. In the same way, inflation might have left behind gravitational ridges so vast they extend beyond our cosmic horizon, tugging at everything within reach. This idea turns dark flow from a puzzle into a potential time capsule. The coordinated motion of galaxy clusters wouldn't be caused by some unseen structure in the present, but by the gravitational memory of the universe's most violent moment. It's like finding a compass needle pointing not north, but toward the spot where the universe took its first breath. Some models even suggest these primordial imbalances could have created superstructures beyond our view, cosmic continents so massive they make our entire observable universe look like a speck of dust on their shoreline. Yet not all scientists are convinced. Critics argue that inflation should have smoothed out such dramatic irregularities, leaving the universe far more uniform than dark flow implies. After all, inflation's entire purpose was to homogenize the cosmos, erasing any drastic imbalances. If dark flow is real, it might mean inflation wasn't the flawless process we've assumed, or that it operated under rules we haven't yet uncovered. The debate cuts to the heart of cosmology itself. If dark flow is a relic of inflation, it's not just a curiosity, it's a direct line to the universe's first moments, a clue about how space-time behaved when reality was still taking shape. But if it's something else entirely, the implications are even wilder. Either way, one thing is clear: the universe's earliest seconds hold secrets that still shape its destiny billions of years later. And dark flow might be the thread that ties them together. Here's something that might change how we see the entire cosmic puzzle. Dark flow could be tangled up with one of the biggest headaches in modern cosmology, the Hubble tension. For years, scientists have been getting two different answers when they measure how fast the universe is expanding. One method, using nearby stars and galaxies, gives a certain number. Another, peering back at the ancient light of the cosmic microwave background, gives a slightly smaller one. At first glance, that difference might seem trivial, but in the precise world of astrophysics, it's a glaring discrepancy. Now imagine if dark flow is the reason for that mismatch, if our local patch of the universe isn't just expanding but also being dragged along by this mysterious current, subtly throwing off our measurements like a boat caught in a hidden tide. Think of it like standing on a moving walkway while trying to measure the speed of people around you. If you don't realize the ground itself is shifting, your calculations will be off. That's the essence of the Hubble tension connection. If dark flow is real and our galaxy and its neighbors are caught in this cosmic undertow, it means we're not seeing the universe's true expansion. We're seeing expansion plus motion from an unseen force. Suddenly, those conflicting numbers start to make sense. The local measurements influenced by dark flow would show a slightly higher expansion rate, while the ancient light from the early universe, unaffected by this later motion, would tell a different story. But here's where it gets even more intriguing. Some researchers suggest dark flow might not just be skewing our measurement, it could be revealing a deeper layer of cosmic structure. What if the universe isn't expanding uniformly because of vast, uneven gravitational fields we've yet to map? Or worse, what if our entire observable universe is just a tiny bubble inside something far larger, where the rules of physics operate differently? The Hubble tension might be the first clue that we're not seeing the full picture, that dark flow is just the tip of an iceberg so colossal it redefines reality itself. Of course, not everyone's convinced. Skeptics argue that the Hubble tension could stem from errors in our techniques or gaps in our understanding of dark energy. After all, measuring the universe is like assembling a jigsaw puzzle with half the pieces missing. It's easy to misinterpret the shapes, but if dark flow and the Hubble tension are connected, it would mean we're on the verge of something revolutionary. Not just a tweak to our models, but a wholesale reimagining of how the cosmos works. So the next time you hear about scientists arguing over the universe's expansion rate, remember, it's not just about numbers. It's about the possibility that we're caught in a cosmic current, one that's pulling us toward answers far stranger than we ever expected. And that's the beauty of astronomy. Even our uncertainties point the way to new frontiers. Galaxy clusters are more than just cosmic landmarks. They're the universe's way of pointing us toward its deepest mysteries. When astronomers track their motion across the void, they're not just mapping random drift. They're following breadcrumbs, a trail of movement so precise it defies coincidence. Picture hundreds of these colossal clusters, each containing thousands of galaxies, all drifting in the same direction like leaves caught in a silent wind. The odds of this happening by chance are astronomically low. This isn't just scattered motion, it's a coordinated flow, a current in the cosmic ocean with a source we can't yet see. What makes this evidence so compelling is the sheer scale of consistency. From the Hydra Centaurus supercluster relatively close by to structures billions of light-years away, the pattern holds. It's as if someone drew an invisible arrow across the sky, and every massive object in its path obediently followed. Scientists measure this motion using the cosmic microwave background as a fixed reference point, like surveying the movement of ships against a distant shoreline. The clusters aren't just moving, they're moving faster than the universe's expansion should allow, as if something out there is reeling them in. The precision of these measurements is staggering. By analyzing subtle distortions in the cosmic microwave background caused by the cluster's hot gas, a phenomenon called the kinematic Sunyaev-Zel'dovich effect, researchers can detect motions as slow as 600 miles per second across mind-bending distances. That's like spotting a snail's crawl from orbit. Yet despite this painstaking work, the source of the pull remains frustratingly out of view, lurking somewhere beyond the cosmic horizon where light from the early universe hasn't had time to reach us. Some argue this could still be a statistical fluke, that we're connecting dots that don't truly form a line, but the data speaks volumes. When independent teams using different instruments, from the Planck satellite to ground-based telescopes, keep finding the same peculiar motion, it's hard to dismiss as error. The clusters aren't just whispering to us, they're shouting that there's something extraordinary out there, something so massive it bends the rules of cosmic motion on scales we're only beginning to comprehend. And that realization changes everything, because if the universe is sending us signals this bold, the least we can do is keep listening. We've always thought of the observable universe as the ultimate frontier, a sphere of space stretching roughly 93 billion light-years in every direction, containing everything we could possibly see or study. It's a comforting boundary, the cosmic equivalent of standing on a shoreline and knowing the ocean extends only as far as the horizon. But dark flow shatters that illusion. If galaxy clusters are being pulled toward something beyond that horizon, it means the universe doesn't end where our vision does. There's an unseen landscape out there, vast and mysterious, exerting its influence like a distant mountain range bending the path of a river we can't yet see. This realization forces us to confront a humbling truth. The cosmos we've mapped so meticulously might just be a speck in something far grander. Imagine you're inside a giant balloon with the inner surface representing everything we can observe. No matter how much you study that surface, you'd never know about the room outside unless, say, the balloon started rolling toward something. That's the essence of dark flow. The motion of galaxy clusters is our first clue that the room exists, that there's an outside to our cosmic bubble. And whatever's out there isn't just passively sitting in the dark, it's massive enough to tug entire clusters of galaxies off course. The irony is crushing. For centuries, we've built telescopes to peer deeper into space, assuming that with enough time and technology, we could uncover all its secrets. But dark flow suggests some answers might forever lie beyond our grasp, hidden by the very physics that govern light and time. The edge of the observable universe isn't a wall, it's a curtain, and behind it, something enormous is moving the furniture. Some theories propose that this unseen mass could be a superstructure of staggering proportions, a cosmic continent so vast it makes our entire observable universe look like an island in its shadow. Others wonder if it's evidence of a multiverse, where neighboring universes exert gravitational pull on our own like ships passing in the night. Yet here's the twist: even if we accept that something lurks beyond the horizon, we may never know its true nature. Light from those regions hasn't reached us yet, and because the universe is expanding faster than light can travel across it, it never will. We're left studying shadows, inferring the shape of giants from the way they bend the light around them. It's like trying to reconstruct a storm by watching how it makes the trees sway. The harder we look, the clearer it becomes that dark flow isn't just a mystery, it's a mirror, reflecting the limits of human curiosity itself. And that's the most thrilling part, because in the end, the universe doesn't owe us answers. It simply invites us to keep asking better questions. Supercomputers are the cosmic laboratories of the 21st century, where scientists recreate realities we can't yet observe. To unravel the mystery of dark flow, researchers feed these machines with mind-bending scenarios colliding universes, remnants of a time before the Big Bang, even higher dimensional structures bending gravity in ways Einstein never imagined. One simulation might model our universe as a bubble brushing against another in the multiverse, their gravitational interaction sending ripples through space-time. Another could explore the idea of cosmic defects, wrinkles left over from the universe's birth, like scars on the fabric of reality itself. The goal isn't just to match the observed motion of galaxy clusters, but to ask a far more radical question. What would the universe have to look like for dark flow to make sense? The results are as fascinating as they are inconclusive. Some simulations show that if another universe grazed ours during inflation, the gravitational disturbance could create a coordinated flow of matter on scales we see today. Others suggest that if the Big Bang wasn't perfectly symmetrical, if space-time had a slight tilt from the very beginning, it might have set entire superclusters adrift in the same direction. But here's the catch. While these models produce flows resembling dark flow, none perfectly replicate the staggering speeds and coherence seen in the actual data. It's like finding a key that almost fits a lock close enough to suggest you're on the right track, but not quite turning the mechanism. What makes these simulations invaluable isn't their failures, but how they reshape the search. Every dead end rules out a class of possibilities, narrowing the field like a cosmic game of 20 questions. When a collision with another universe can't account for the observed flow, it steers theorists toward alternative explanations, like primordial magnetic fields or undiscovered particles altering gravity on colossal scales. Supercomputers act as time machines in reverse, letting us test theories that would otherwise exist only on chalkboards or in the minds of daring physicists. The most provocative simulations explore ideas that sound like science fiction. One team modeled a scenario where our universe is embedded in a higher dimensional space, with gravity leaking in from adjacent dimensions. Another recreated the hypothetical ekpyrotic model, where the Big Bang was actually a collision between two four-dimensional membranes in a five-dimensional bulk. While these concepts stretch credulity, they demonstrate the sheer creativity required to explain dark flow. After all, when the universe hands you a paradox this profound, conventional thinking won't cut it. Yet for all their power, simulations have limits. They can't tell us what lies beyond the cosmic horizon any more than a ship's wake can reveal the ocean's far shore. What they do provide is a compass, a way to distinguish between wild guesses and testable hypotheses. As supercomputers grow more powerful and algorithms more sophisticated, each simulation brings us closer to the day when dark flow stops being a mystery and starts being a roadmap, one that might lead us to discoveries rewriting the very laws of physics. Until then, every line of code, every virtual universe, is a step toward understanding the most humbling truth of all. That reality might be far stranger than our boldest simulations dare to suggest. Not every scientist is convinced dark flow exists. Some argue it might be a cosmic mirage, a trick of the data rather than a genuine phenomenon. The skeptics raise valid points. When you're measuring movements across billions of light years, even the tiniest errors can create illusions of patterns that aren't really there. Imagine trying to track the wind by watching leaves flutter in a storm. Some leaves might seem to move together, but is it the wind or just random chance? That's the heart of the debate. Could dark flow be the result of overlooked quirks in how we interpret the cosmic microwave background? Or might local gravitational influences, like nearby superclusters we haven't fully mapped, be nudging galaxies in ways that mimic a larger, mysterious pull. One major criticism centers on the kinematic Sunyaev-Zel'dovich effect itself, the very tool used to detect dark flow. This method relies on passing incredibly subtle distortions in the afterglow of the Big Bang, a signal already drowned in noise from intervening gas, dust, and other cosmic clutter. Some researchers suggest that what looks like a coordinated flow could instead be the accumulated tug of countless smaller structures, their combined effect masquerading as something grander. It's like hearing a chorus and mistaking it for a single, powerful voice. Even the teams behind the original dark flow findings admit the signal is faint, hovering at the edge of what's statistically significant. In science, extraordinary claims require extraordinary evidence, and not everyone agrees the evidence is there yet. Then there's the challenge of perspective. Our view of the universe is inherently limited. We're seeing snapshots of galaxies at different moments in their history, not a real-time motion picture. Combine that with the fact that we're stuck in a single vantage point, like trying to map ocean currents from a single buoy, and the room for error grows. Critics point out that alternative methods for measuring large-scale motions, like tracking galaxy redshifts, haven't consistently reproduced the dark flow signal. If the phenomenon were as universal as proposed, shouldn't it show up everywhere we look? The inconsistency fuels doubts, yet the debate itself is a testament to how science thrives on skepticism. Every challenge pushes researchers to refine their methods, to build better instruments, to question assumptions. Missions like the Euclid Space Telescope and next-generation cosmic microwave background experiments aim to settle the argument with unprecedented precision. Whether dark flow is confirmed or debunked, the controversy has already done something vital. It's forced us to confront the limits of our cosmic maps and the audacity of our theories. Because in the end, the universe doesn't care what we believe it simply is. And the only way forward is to keep looking, measuring, and daring to ask questions that might upend everything we think we know. The next generation of space telescopes is about to turn the mystery of dark flow into a solvable equation. With instruments like the European Space Agency's Euclid and NASA, a Nancy Grace Roman Space Telescope set to launch in the coming years, scientists are arming themselves with tools powerful enough to either crack this cosmic case wide open or finally put it to rest. These aren't just incremental upgrades, they're paradigm shifts, capable of mapping the universe with such precision that even the faintest whispers of dark flow will be impossible to ignore. Imagine swapping out a blurry black and white photograph for a high-definition 3D scan of the cosmos. That's the leap we're talking about. Euclid, in particular, is designed to be a dark flow detective. Over 6 years, it will survey nearly a third of the sky, measuring the shapes and motions of billions of galaxies with an accuracy never before achieved. Its secret weapon, the ability to trace the invisible scaffolding of dark matter by watching how its gravity bends light from distant objects, a technique called weak gravitational lensing. If dark flow is real, Euclid won't just see the current dragging galaxies along. It might reveal the hidden structure responsible, like tracking a river's path by the way it distorts the landscape around it. Meanwhile, the Roman Space Telescope will peer even deeper into cosmic history, capturing infrared images so sharp they could spot the gravitational shadows of superstructures lurking beyond our observable universe. But these missions aren't just about confirming or debunking dark flow. They're about rewriting the rules of cosmology itself. If the data confirms galaxies are truly being pulled by something beyond our horizon, it would force us to grapple with realities like multiverses or higher dimensions. If instead the phenomenon vanishes under sharper scrutiny, we'll have to confront an equally profound question. Why did the universe appear to behave so strangely in the first place? Either outcome sends shockwaves through our understanding of space and time. What makes this moment so thrilling is the sheer potential for surprise. History shows that whenever we build tools to test one big idea, like whether the Earth orbits the Sun or if black holes exist, we stumble onto discoveries nobody predicted. Dark flow could be the same. Even if it turns out to be a cosmic mirage, the missions designed to study it will expose truths about dark matter, galaxy formation, and the universe's expansion that we can't yet imagine. Because that's how science works at the frontier. You set out to answer one question, and the universe hands you a dozen more, each more fascinating than the last. And that's the real prize, not just solving the mystery, but discovering how much bigger the mystery really is. If dark flow is real, it doesn't just hint at unseen forces, it rewrites the entire cosmic playbook, turning our universe from a solitary stage into a single act in a multiverse epic. Picture a soap bubble floating in a sink full of them, each one a self-contained universe with its own laws of physics, its own history, its own destiny. Now imagine that these bubbles aren't just drifting aimlessly, they're close enough to interact, their surfaces brushing against one another, their gravitational fields reaching across the void. That's the breathtaking possibility dark flow forces us to consider. Our universe might not be alone, and whatever lies beyond its edges could be shaping its future in ways we're only beginning to glimpse. This isn't just about adding another layer to the cosmic map. It's about redefining what the universe's fate even means. For decades, we've assumed the cosmos had two possible endings: the Big Freeze, where expansion stretches matter so thin that stars flicker out and galaxies evaporate into darkness, or the Big Crunch, where gravity eventually reverses the expansion, pulling everything back into a singularity. But dark flow throws a third option onto the table: the Big Pull. If galaxy clusters are being dragged towards something beyond our horizon, it suggests the universe isn't just expanding or contracting, it's migrating, caught in a current that could lead to collisions with other universes, or even absorption into something unimaginably larger. The implications are dizzying. A multiverse wouldn't just be a collection of isolated bubbles, it could be a dynamic ecosystem, with universes merging, splitting, or influencing one another across dimensions. Some theories suggest that what we're seeing as dark flow might be the gravitational wake of a neighboring universe that brushed past ours in the distant past, like a ship passing close enough to tug another off course. Others propose that our universe could be embedded in a higher dimensional space, where gravity leaks in from other realms, creating flows that defy our three-dimensional logic. But here's the twist: if dark flow is pulling us toward something, it might not be a gentle journey. Simulations of colliding universes suggest these encounters could unleash energies beyond comprehension, warping space-time itself. Imagine two soap bubbles merging. The surface tension doesn't just vanish. It creates ripples, distortions, chaotic rearrangements. On a cosmic scale, that could mean bursts of radiation, sudden shifts in fundamental constants, or even the birth of new physical laws. It's a reminder that the universe's story might not have a quiet ending. The final chapter could be a collision, a merger, or a transformation we can't yet fathom. Yet for all the drama, dark flow might also offer a strange kind of cosmic comfort. If we're part of something bigger, it means the universe isn't just a lonely, cooling ember. It's a thread in a tapestry vaster than we ever dreamed. Every galaxy caught in this mysterious current is a reminder that the cosmos still has secrets to share, and that the greatest discoveries might lie not in the stars we see, but in the darkness just beyond. Dark flow doesn't just challenge our models of the universe, it forces us to reckon with the very nature of knowledge itself. For centuries, humans have looked to the stars and assumed that with enough time and ingenuity, we could unravel every cosmic secret. But what if some answers lie forever out of reach, hidden beyond the edge of our observable universe? The possibility that forces outside our reality could be tugging at galaxies like puppet strings is humbling. It suggests that no matter how advanced our telescopes or brilliant our theories, there might always be shadows we can't illuminate, a cosmic, here be dragons, lurking just beyond the maps we've drawn. This isn't just a scientific dilemma, it's a philosophical earthquake. Think about how we've historically approached the unknown. When early navigators encountered uncharted waters, they didn't assume the ocean ended, they knew their maps were incomplete. Dark flow poses a similar challenge, but with a twist. The uncharted waters might be fundamentally unreachable, separated from us by the relentless expansion of space itself. The light from whatever's pulling those galaxies will never reach us, no matter how long we wait. That means we're left with a haunting question. Are we like explorers confined to a single island, forever speculating about continents we can't sail to? Yet there's another way to see this. Every major leap in human understanding has come from confronting the limits of what we thought was possible. When Einstein shattered Newton's clockwork universe with relativity, or when quantum mechanics revealed a world where particles could be in two places at once, we didn't abandon science, we expanded it. Dark flow could be the next frontier in that tradition, a signal that our current physics is merely the opening chapter of a much stranger story. The idea that we might never fully grasp reality isn't a surrender. It's an invitation to keep pushing, to redefine what understanding even means. Consider the history of cosmic horizons. Not long ago, astronomers believed the Milky Way was the entire universe. Then Edwin Hubble proved galaxies existed beyond our own, and suddenly the cosmos grew exponentially. Dark flow might be another horizon moment, hinting at realities so vast they make our current universe seem small. The difference is, this time the horizon isn't just distant, it's fundamentally invisible, a wall built by the speed of light and the expansion of space. That doesn't mean we stop looking. It means we get creative, searching for indirect clues like detectives piecing together a case from circumstantial evidence. Some argue this is the essence of science, not the illusion of final answers, but the thrill of the chase. The universe owes us nothing, yet it keeps offering puzzles, dark flow being one of the most tantalizing. Whether it leads us to a multiverse, a flaw in our gravity equations, or something even wilder, the journey matters as much as the destination, because in the end, the cosmos isn't just a puzzle to solve. It's a conversation, one where every discovery leads to deeper questions, and every limit we hit is just the starting point for the next great leap. And that's what makes this moment so extraordinary. We're not just studying the universe, we're learning how to listen to it. It's easy to lump dark flow together with dark matter and dark energy after all. They all share that ominous, dark label, hinting at mysteries we can't directly see. But here's the crucial difference. While dark matter and dark energy work within the universe, dark flow seems to be pulling from beyond it. Think of it like this. Dark matter is the invisible scaffolding holding galaxies together. Dark energy is the mysterious force pushing the universe apart, but dark flow. That's the cosmic equivalent of feeling a tug on your sleeve from someone standing outside the room. It's not just another piece of the puzzle, it's a hint that the puzzle might be far bigger than we thought. One common misconception is that dark flow is simply dark matter's gravity acting on a larger scale. But the math doesn't add up. Even if you accounted for every invisible speck of dark matter in the observable universe, Its collective pull couldn't explain why galaxy clusters are racing toward the same distant point at millions of miles per hour. Dark flow's motion is too coordinated, too directed, as if something out there, something beyond our cosmic horizon, is calling the shots. It's like watching compass needles all point north, only to realize north isn't even on your map. Then there's the confusion with dark energy. While dark energy drives the universe's expansion, it does so uniformly, like a rising loaf of bread where every raisin representing a galaxy moves away from every other raisin. Dark flow, on the other hand, is more like a handful of raisins suddenly sliding toward one edge of the pan. That's not expansion, it's a cosmic current, and it suggests forces at work that defy our current understanding of how space behaves. Part of the confusion stems from how these discoveries unfolded. Dark matter was proposed in the 1930s to explain why galaxies spin faster than they should, while dark energy emerged in the late 1990s to account for the universe's accelerating expansion. Both became cornerstones of cosmology, woven into textbooks and documentaries. Dark flow, though, arrived in 2008 as an uninvited guest, challenging the very framework those other, dark phenomena helped build. It's not just another invisible actor in the cosmic play, it's a plot twist, one that forces us to question whether the stage itself extends farther than we ever imagined. This distinction matters because it shapes how we interpret the universe's fate. If dark flow is real, it's not enough to study what's in the cosmos. We have to ask what's outside it. That's why this isn't just another technical debate among astronomers. It's a revolution in the making, one that could redefine our place in the grand scheme of things. And that's the beauty of science. Sometimes the most profound discoveries begin with a simple question. Wait, why is everything moving that way? History has a funny way of repeating itself in science, not in the details, but in the way a single anomaly can shatter centuries of certainty. When Galileo first pointed his telescope at Jupiter in 1610 and saw moons orbiting something other than Earth, it wasn't just a discovery, it was a revolution, proof that the universe didn't revolve around us. Fast forward to the 1920s, when Edwin Hubble noticed distant galaxies weren't just floating in space, they were racing away from us, revealing an expanding universe where static, eternal heavens were just an illusion. These weren't minor corrections to the textbooks, they were seismic shifts, moments when humanity realized the cosmos was far stranger than we'd ever dared to dream. Now, dark flow stands poised to join that elite club of game changers. Like those historic discoveries, it starts with an observation that doesn't fit galaxies moving where they shouldn't, defying the neat equations we've written to explain cosmic motion. And just like Galileo's moons or Hubble's redshift, the implications ripple far beyond the initial anomaly. If confirmed, dark flow wouldn't just add another line to the list of cosmic mysteries, it would tear open a new chapter in our understanding of reality, forcing us to grapple with forces or realms beyond the universe we know. Consider the pattern. Every time we've assumed we've mapped the limits of the cosmos, the universe laughs and shows us another layer. Newton's clockwork mechanics gave way to Einstein's warped space-time, which in turn bent to accommodate quantum uncertainty. Dark flow fits right into this tradition of humble pie, reminding us that our models are always provisional, always awaiting the next anomaly that will append them. Even the term dark flow echoes this legacy like dark matter and dark energy. It's a placeholder, a label for something we can detect but not yet define. What makes this moment so electrifying is the sheer scale of possibility. Galileo's discovery challenged Earth's centrality. Hubble's revealed a dynamic cosmos. Dark flow, though, hints at something even more profound. that our universe might not be a solitary island, but part of an archipelago of realities, each with its own rules. It's the difference between realizing you live in a village and discovering your village is just one dot on a globe. The irony is delicious. The more we learn, the more we grasp how little we know. And that's the real lesson history teaches us, not just about the universe's secrets, but about the audacity of human curiosity. Because every paradigm shift begins with someone daring to ask, wait, why doesn't this add up? Gravity may be the weakest of nature's fundamental forces, but its influence stretches across the cosmos, bending light, anchoring galaxies, and sculpting the very fabric of space-time. Yet dark flow reveals a tantalizing crack in our understanding of this familiar force. If galaxy clusters are being dragged toward some unseen horizon, it implies gravity isn't just acting within our universe, it might be reaching beyond it, threading through dimensions or realities we can't yet perceive. This isn't just a tweak to Einstein's theory of relativity. It's a seismic shift, suggesting gravity could operate on scales so vast they defy our current equations. Consider how gravity works in our everyday cosmos. A planet orbits a star because space-time curves around the star's mass, like a marble rolling around a funnel. Galaxies cluster together because dark matter's invisible pull overcomes the universe's expansion, creating a cosmic web of filaments and voids. But dark flow doesn't fit this picture. The motion of these galaxy clusters isn't just a local dance, it's a synchronized march toward something outside the web, something whose gravitational reach extends farther than relativity predicts. It's as if we've been studying ripples in a pond, only to realize the waves are being pulled by a tide from another ocean entirely. One radical possibility is that gravity leaks into our universe from higher dimensions or neighboring realities. String theory, for instance, suggests our cosmos might be a three-dimensional membrane floating in a higher dimensional space, with gravity acting as the only force able to traverse those hidden realms. If true, dark flow could be the tug of a parallel universe's gravity, warping our space-time from afar. Imagine two bedsheets hanging side by side. If one sags, it could pull the other slightly toward it without the sheets ever touching. That's the kind of indirect influence we might be witnessing on a cosmic scale. But there's a humbler explanation. Einstein's theory, while spectacularly accurate in our observable universe, might need revision for extremes of distance or scale. After all, Newton's laws worked perfectly until they didn't, until Mercury's orbit around the Sun revealed a flaw that only relativity could fix. Dark flow might be our modern Mercury moment, a clue that gravity's rules change when applied to structures spanning billions of light years. Some theorists propose modifications to relativity, like adding terms that account for unseen mass or hidden dimensions, but these ideas remain untested. The irony is profound. Gravity, the force we thought we knew best, the one that grounds us to Earth and guides the planets, might be the very thing hiding the universe's deepest secrets. Whether dark flow reveals a flaw in our equations or a window into the multiverse, one thing's certain: the cosmos is far stranger than gravity alone can explain. And that's the beauty of the mystery. Every anomaly, every inconsistency, is a signpost pointing toward truths we've yet to uncover. So while gravity shapes the universe we see, dark flow hints at the invisible hands shaping gravity itself. Quantum mechanics and cosmic scales seem to occupy opposite ends of reality, one governing the bizarre behavior of particles so small they barely exist, the other dictating the motion of galaxies across unfathomable distances. Yet dark flow blurs this divide, forcing us to ask whether the universe's largest structures might somehow echo its smallest quirks. Picture this: in the quantum realm, particles vanish and reappear, communicate instantaneously across space, and exist in multiple states at once. Now imagine those same rules stretched to cosmic proportions. Could dark flow be the universe's way of showing us that quantum weirdness doesn't just live in atoms, it shapes the fate of galaxies? The idea isn't as far-fetched as it sounds. Quantum fluctuations during the universe's infancy left imprints on the cosmic microwave background, tiny ripples that eventually grew into galaxies and clusters. If those early fluctuations weren't perfectly random, if some hidden quantum bias tilted the scales, it might explain why vast swaths of the cosmos are now streaming in unison. Think of it like rolling dice billions of times and always getting slightly more sixes. Over time, that tiny imbalance could snowball into something as dramatic as dark flow. Some theorists even speculate that quantum entanglement, that spooky connection between particles, might operate on galactic scales, linking clusters across billions of light years in a coordinated dance. But here's the twist: gravity, the force we usually blame for large-scale motion, struggles to explain dark flow's sheer coherence. Quantum effects, though, thrive on synchronization. In superconductors, electrons pair up and move in perfect harmony. In superfluids, atoms flow without friction. Could dark flow be a cosmic superfluid, with galaxies sliding toward some quantum attractor we can't yet see? The math is speculative, but the parallels are tantalizing. Even the fabric of space-time itself, once thought smooth and continuous, might be pixelated at the tiniest scales. A foam of quantum bubbles whose turbulence influences everything from black holes to galaxy clusters. Of course, not everyone's convinced. Critics argue that quantum mechanics and general relativity, the twin pillars of modern physics, refuse to play nice, and dark flow might just highlight their incompatibility. After all, relativity paints gravity as a smooth curve in space-time, while quantum theory insists everything is jittery and discrete. Bridging these two visions has been physics' holy grail for a century, and dark flow could be the clue that finally cracks the code. Or it might be a red herring, a cosmic illusion born from our incomplete understanding of how gravity truly works on the largest scales. What's undeniable is this: dark flow forces us to confront the uncomfortable truth that our universe might not obey separate rulebooks for the very big and the very small. The same quantum strangeness that baffles us in labs could be writ large across the cosmos, hidden in plain sight. Whether that's the key to unlocking dark flow or just another dead end, one thing's certain: the universe loves reminding us that the most profound mysteries often lie at the intersections of ideas we thought were worlds apart. Dark flow isn't just a cosmic anomaly, it's a story waiting to be told, a blank canvas for the human imagination. Science fiction has always thrived on the unknown, and few mysteries are as tantalizing as the idea of an unseen force dragging galaxies toward some unfathomable horizon. Novels like Alastair Reynolds' House of Suns play with the concept of vast, invisible structures shaping the cosmos, while films and documentaries borrow dark flow's eerie premise to explore existential questions. Are we alone? Is our universe just one of many? The very phrase dark flow sounds like something ripped from a thriller, evoking a sense of creeping dread. The universe isn't just expanding, it's being pulled. Documentaries have seized on this tension, framing dark flow as the ultimate cosmic cliffhanger. When the BBC's Universe series delves into the phenomenon, it's not just presenting data, it's crafting a narrative of discovery and doubt, with scientists as detectives chasing shadows. Even YouTube creators lean into the mystery, using dark flow as a springboard for speculation. Is it evidence of a higher dimensional being, a glitch in the simulation? The beauty of these stories lies in their ability to straddle the line between fact and fantasy. turning raw data into something visceral. Because let's face it, there's something deeply unsettling about the idea that everything we know might be caught in a current we can't see or understand. But dark flow's cultural resonance goes beyond fiction. It taps into a primal fascination with the hidden, the just out of reach. Ancient myths spoke of cosmic rivers carrying souls to the afterlife. Modern sci-fi replaces those rivers with dark flow. A 21st century Styx guiding galaxies instead of spirits. Even video games like Elite Dangerous and No Man's Sky weave similar themes, letting players explore universes where unexplained forces warp the fabric of space. These aren't just Easter eggs for science nerds, they're proof of how deeply dark flow has embedded itself in our collective psyche. A symbol of the infinite mysteries lurking beyond the edge of our maps. What makes dark flow such a potent muse is its duality. It's real enough to fuel peer-reviewed papers, yet elusive enough to inspire wild speculation. Scientists might see equations and error margins, but storytellers see something richer, a metaphor for humanity's place in the cosmos. We're like sailors on a ship, feeling the tug of a current we can't see, wondering if it leads to paradise or oblivion. And perhaps that's the real power of dark flow, not just as a scientific puzzle, but as a mirror. However the mystery resolves, one thing's certain: the universe has always been our greatest storyteller, and dark flow is its latest plot twist. The hunt for dark flow isn't just about data and equations. It's about the people staring into the cosmic abyss, wrestling with questions that defy easy answers. Take Dr. Laura Mersini-Horton, a theoretical physicist who's spent years probing the edges of our universe. For her, dark flow isn't just an anomaly, it's a potential window into the multiverse. When we first saw those galaxy clusters moving in unison, she explains, it felt like catching a glimpse of something bigger, like discovering your house has a secret door and you've just found the key. Her enthusiasm is contagious, but so is her caution. The hardest part, knowing we might never get a clear answer. The thing pulling those galaxies could be forever out of reach, like a shadow you can't chase down. Then there's Dr. Alexander Kashlinsky, the astrophysicist whose team first identified dark flow in data from the Wilkinson microwave anisotropy probe. For him, the discovery was equal parts triumph and frustration. Science loves a tidy story, he says, but dark flow refuses to fit. Every time we think we've accounted for errors, local clusters, measurement noise, the signal sticks. It's like the universe is teasing us. His work has faced fierce skepticism, and he welcomes it. Good science isn't about being right, it's about asking better questions. If dark flow pushes us to rethink gravity or the Big Bang, that's progress even if it turns out to be a dead end. The human side of this quest shines through in stories like Dr. Priyamvada Natarajan's, a cosmologist at Yale. She recalls late nights poring over simulations, tweaking variables to see if anything could replicate the observed flow without invoking unseen universes or new physics. There's a moment, she says, when you realize you're not just crunching numbers, you're eavesdropping on the universe's deepest secrets, and sometimes it whispers back in ways that give you chills. Her candor about the emotional roller coaster, the thrill of a hunch paying off, the gut punch of a dead end reveals science as it truly is, a deeply human endeavor. What unites these researchers isn't just their expertise, but their willingness to sit with uncertainty. Dr. Ethan Siegel, a science communicator and astrophysicist, puts it bluntly: dark flow is the kind of mystery that keeps scientists up at night. It's not just about what we know, it's about what we're allowed to know. The universe might have built in limits to our curiosity, and that's humbling. Yet even in the face of those limits, the drive to understand never falters. As Dr. Mersini Horton puts it, maybe we'll never see what's pulling those galaxies. But the fact that we noticed the tug, that's a triumph. It means we're paying attention. And in the grand search for cosmic truths, that attention, that stubborn, starry-eyed curiosity, might be the most powerful tool of all. Dark flow isn't just a cosmic mystery, it's a masterclass in scientific humility, a living lesson that the universe refuses to be confined by our textbooks. Picture a classroom where students learn that Newton's laws or Einstein's relativity are the final word on gravity, only to discover that galaxy clusters are racing toward some unseen horizon in defiance of those very rules. That's the power of dark flow. It transforms abstract theories into visceral puzzles, showing young minds that science isn't about memorizing facts but about wrestling with the unknown. When a professor points to the night sky and says, "We don't know what's pulling those galaxies," it does something radical. It invites curiosity, not just compliance. This phenomenon teaches a deeper truth about the scientific process itself. For centuries, we've built models to explain the cosmos, only to watch them crumble under new discoveries. Dark flow is the latest in that lineage, proving that even our most cherished theories are provisional, always awaiting the next anomaly. Take the cosmological principle, the idea that the universe is uniform on large scales. Dark flow throws sand in those gears, suggesting that beyond our horizon, reality might be lopsided, tugged out of shape by forces we can't see. For students, that's electrifying. It turns science from a static catalogue of answers into a dynamic detective story, where every solved mystery reveals 3 new ones. The beauty of dark flow as a teaching tool lies in its openness to interpretation. Is it evidence of a multiverse, a flaw in our gravity equations, a relic from before the Big Bang? Each possibility becomes a doorway to different branches of physics, from quantum mechanics to string theory. A single anomaly becomes a springboard for critical thinking, forcing students to weigh evidence, challenge assumptions, and embrace uncertainty. Imagine a lab where instead of following step-by-step instructions, learners are handed data on galaxy motions and asked, "What's your hypothesis?" That's the kind of creative rigor dark flow inspires. The kind that doesn't just fill minds but ignites them. And let's not forget the human element. Dark flow embodies the stubborn curiosity that drives science forward. When researchers like Alexander Kashlinsky first published their findings, they faced skepticism, even ridicule. Yet they persisted, refining methods, rechecking data, daring to ask questions others dismissed. That's the real lesson for students. Breakthroughs don't come from memorizing formulas, but from daring to say, "This doesn't make sense, let's find out why." Dark flow reminds us that science's greatest victories often start with its messiest mysteries, the ones that refuse to fit neatly into our models. Ultimately, dark flow does more than challenge theories. It reshapes how we think about discovery itself. In a world obsessed with quick answers, it's a testament to the value of unanswered questions. Whether it's a high school physics class or a graduate seminar, this cosmic enigma teaches the same timeless truth. The universe is under no obligation to make sense to us. And that's not a flaw in science, it's the very thing that makes it thrilling. Because when the cosmos hands us a paradox like dark flow, it's not just testing our knowledge. It's inviting us to dream bigger. The quest to unravel mysteries like dark flow forces us to confront a dilemma as old as science itself. How much should humanity invest in chasing cosmic curiosities when urgent earthly problems demand attention? Telescopes like Euclid and the Roman Space Telescope cost billions, their construction spanning decades and continents. These aren't just instruments, they're bets placed on the future. gambles that understanding the universe's hidden architecture will pay dividends we can't yet imagine. But with climate crises, pandemics, and inequality pressing in, how do we justify such monumental expenditures? The answer lies in recognizing that cosmic research isn't a luxury. It's a mirror reflecting our priorities, our collaboration, and our resilience as a species. Consider the International Space Station, a project once dismissed as a boondoggle. Today, it's a blueprint for global cooperation, proving that nations can unite around shared scientific goals despite political divides. Dark flow research operates on similar principles. It requires data sharing across borders, telescopes in remote locations from Chile to Antarctica, and supercomputers crunching numbers day and night. These collaborations don't just produce papers, they forge relationships and technologies with unexpected spin-offs. The same algorithms used to map galaxy clusters now help track deforestation, while precision optics developed for space telescopes improve early cancer detection. When we invest in cosmic mysteries, we're not just buying answers, we're building capacity to solve terrestrial challenges in ways we can't predict. Yet the ethical calculus grows thornier when we ask who benefits. Most cutting-edge observatories are funded by wealthy nations, yet their data belongs to humanity. Should a farmer in rural India care about galaxy clusters? Perhaps not directly, but the same systems monitoring dark flow also track asteroid threats and solar storms that could disrupt global agriculture. There's also the democratizing power of inspiration. A child in Nairobi or Lima, gazing at Euclid's discoveries, might see not just stars but a future in STEM. The real ethical failure isn't spending on cosmic research, it's failing to ensure its fruits uplift all of humanity, not just an elite few. Critics argue that dark flow is an intellectual indulgence, a puzzle with no practical application. But history disagrees. When Einstein scribbled equations about warped space-time, no one imagined they'd one day calibrate GPS satellites. The lasers probing gravitational waves today evolved from theoretical musings about black holes. Curiosity-driven science has a habit of sparking revolutions often where we least expect them. Dark flow might not put food on tables tomorrow, but the technologies and collaborations it fosters could reshape our world in ways as unimaginable as smartphones would have been to Galileo. The deeper ethical question isn't whether we should study the cosmos, but how we distribute both its burdens and rewards. When a telescope rises on a sacred mountaintop, who consulted the indigenous communities below? When data flows to prestigious universities, how do we ensure scientists from the global south aren't relegated to footnotes? These aren't distractions from the science, they're integral to doing it right. After all, if we're searching for universal truths, shouldn't the search itself reflect the best of humanity? The story of dark flow isn't just about galaxies moving mysteriously. It's about whether we can move ethically, together toward a future where the heavens aren't just studied by a privileged few, but cherished by all. If dark flow is real, if galaxies are truly being pulled by forces beyond our observable universe, it doesn't just reshape cosmology, it rewrites the possibilities for life itself. Astrobiologists have long assumed that life, wherever it exists, evolves in a universe governed by the same fundamental constants we observe: gravity, light speed, the strength of electromagnetism. But what if these constants aren't universal? What if, beyond our cosmic horizon, physics operates differently, and dark flow is our first hint of that diversity? Suddenly, the search for extraterrestrial life isn't just about finding Earth-like planet. It's about grappling with the idea that life might thrive in environments we can't even imagine. Picture a universe where gravity is slightly stronger, where stars burn hotter and faster, where the very chemistry of life follows unfamiliar rules. If dark flow reveals that our cosmos is nudged by external forces, those forces could be shaping other regions of reality in ways that redefine habitability. Astronomers often focus on the Goldilocks zone, the narrow orbital range where planets are neither too hot nor too cold for liquid water. But dark flow suggests a more radical idea, that the Goldilocks zone might extend to entire universes, each with its own unique physics. Life might not just adapt to its planet, it could be molded by the gravitational tides of its cosmos. This isn't pure speculation. We already know life on Earth is influenced by cosmic forces. The Moon's gravity shapes our tides, solar radiation drives mutations. Even the Milky Way's rotation may have guided the evolution of complex molecules. Now scale that up. If galaxy clusters are drifting toward some unseen attractor, the civilizations within them, if they exist, could be subject to forces we've never considered. Imagine a planet orbiting a star caught in dark flow's current, where the night sky isn't static but visibly shifting over millennia, where cosmic expansion isn't just a theory but a tangible force altering ecosystems. For life forms there, evolution might select for traits we'd find incomprehensible, senses tuned to gravitational waves, or biology adapted to a universe in motion. The real mind bender, dark flow might not just affect life's environment, it could alter the very odds of life arising. If the pull of an external universe skews the distribution of matter, some regions might be dense with stars and planets, while others are barren voids. Civilizations could cluster along cosmic currents like fish in a stream, completely unaware of the forces guiding their place in the cosmos. Or worse, what if dark flow's source is a region where physics makes life impossible, and we're witnessing the first ripples of a change that will one day reach us? The search for extraterrestrial intelligence suddenly isn't just about listening for radio signals, it's about mapping the invisible currents that might carry life or snuff it out. Of course, skeptics counter that this is all premature. Without proof that dark flow exists, let alone influences biology, it's a stretch to tie it to astrobiology. But that's the point of frontier science, to ask questions that seem outrageous until they're not. 50 years ago, the idea of extremophiles, life thriving in boiling vents or Antarctic ice, was dismissed as fantasy. Now we know life is far more adaptable than we dreamed. Dark flow challenges us to extend that humility to the cosmic scale. The universe isn't just a stage for life, it's an actor, dynamic and unpredictable. And if we're ever going to understand our place in it, we'll need to stop assuming the rules we know are the only ones that matter. You don't need a billion-dollar telescope to help unravel the universe's deepest mysteries. Some of the most exciting discoveries in cosmology, including clues about dark flow, have come from ordinary stargazers, students, and hobbyists sifting through public data. When NASA and ESA release troves of cosmic microwave background readings or galaxy cluster surveys, they're not just sharing findings, they're inviting the world to join the hunt. Take the story of a retired schoolteacher in Norway who spotted an anomaly in Planck satellite data that professional astronomers had overlooked, or the High School Coding Club in India that helped map peculiar velocities of galaxies using open-source software. These aren't exceptions, they're proof that modern astronomy thrives on collective curiosity. What makes amateur contributions so vital is their sheer volume and diversity. Professional astronomers might focus on narrow questions, but citizen scientists bring fresh eyes and often unexpected expertise. A graphic designer might notice a pattern in galaxy movements that resembles fluid dynamics. A musician could apply waveform analysis techniques to cosmic microwave background noise. Dark flow's detection benefited from this crowdsourced ingenuity. When researchers first published galaxy cluster velocities, online forums lit up with volunteers cross-checking numbers, flagging outliers, and even developing new visualization tools to spot trends. One amateur group created an interactive map of the mysterious motion, making it easier to see the coordinated drift toward the constellation Centaurus, a project that later caught the attention of academic teams. The tools enabling this revolution are more accessible than ever. Platforms like Sunyaev-Zel'dovich host citizen science projects where anyone can classify galaxy shapes or track asteroid trajectories. Free software like Aladdin's Sky Atlas lets users explore archival telescope data, while apps like ESA's Gaia Sky turn smartphones into portable planetariums. For dark flow specifically, amateurs have played key roles in processing data from the Sloan Digital Sky Survey, identifying galaxy clusters with unusual velocities that professional surveys might have missed. It's a modern twist on an old tradition after all. William Herschel discovered Uranus using a homemade telescope, and Caroline Herschel, his sister and collaborator, was an amateur who became the first woman paid for scientific work. But perhaps the most profound impact of amateur astronomy isn't just in the data, it's in the way it democratizes discovery. When a teenager in Brazil or a retiree in Japan helps analyze dark flow signals, they're not just assisting professionals, they're rewriting the script of who gets to participate in science. This collaborative spirit is especially crucial for mysteries like dark flow, where answers might lie in subtle patterns hidden across petabytes of data. No single team, no matter how well funded, can scrutinize every angle, but a global network of curious minds, that's a force capable of spotting the cosmic needles in the haystack. The next breakthrough might not come from a mountaintop observatory, but from someone's laptop halfway across the world. And that's the beauty of science in the digital age. The universe isn't just for experts anymore. It's for anyone willing to look up, dig in, and wonder what's pulling us toward the unknown. The cosmos loves a good mystery-fast radio bursts crackling across space like cosmic Morse code. Black holes merging in gravitational symphonies we can feel but not see. Yet among these enigmas, dark flow occupies a unique place. It doesn't just ask what's in the universe, it questions the very framework of reality itself. Take fast radio bursts, for instance. These fleeting, high-energy signals from distant galaxies are like fireworks, brief, brilliant, and baffling. But once we pinpoint their origins, magnetars colliding neutron stars, they'll slot neatly into astrophysics' existing playbook. Dark flow, on the other hand, resists such tidy explanations. It's not a singular event or exotic object. It's a pattern, a coordinated motion that defies the universe's supposed uniformity. Imagine watching a flock of birds suddenly change direction mid-flight, not because of wind or predators, but because some invisible force beyond the horizon is calling them. That's the scale of disruption dark flow represents. Black hole mergers detected through ripples in space-time are another marvel. These collisions confirm Einstein's predictions with stunning precision, reinforcing our grasp of gravity. But dark flow, it undermines that grasp. When galaxy clusters move faster than relativity allows, it's as if the rulebook's been torn mid-game. Even dark matter and dark energy, those infamous cosmic ghosts, operate within the universe's known boundaries. Dark flow, by contrast, whispers of influences from outside, making it less a puzzle to solve and more a doorway to realms we've yet to imagine. What sets dark flow apart is its sheer audacity. Other mysteries fit within cosmology's current paradigms, waiting for finer details to flesh them out. dark flow doesn't wait, it rewrites. It forces us to consider that the universe might not be the self-contained arena we thought, but a single stage in a multiverse theater with unseen directors pulling strings from the wings. That's why this isn't just another cosmic oddity. It's a challenge to everything we think we know, a reminder that the universe's greatest secrets might not lie in the stars we see, but in the darkness between them. If dark flow isn't just a cosmic fluke but a real phenomenon, the implications are so staggering they rewrite the boundaries of reality itself. Picture our observable universe not as an isolated expanse, but as a single ripple in a pond, one that's being subtly tugged by currents from something far larger. Some physicists speculate this could mean we're part of a super-universe, a structure so vast it makes our 93 billion light-year horizon look like a speck. Imagine standing in a valley and suddenly realizing the mountains around you are just foothills of an unseen, continent-sized range. That's the scale we're talking about, a gravitational influence so immense it operates from beyond the limits of our perception. One of the most compelling theories suggests dark flow could be the gravitational echo of a neighboring universe in the multiverse. Think of it like two ships floating side by side in the ocean. Even if they never touch, their wakes can interact, creating ripples that nudge one another off course. In this scenario, our universe isn't alone. It's brushing up against others in a higher dimensional space, each with its own physics, its own history. The idea isn't as far-fetched as it sounds. String theory, for instance, posits that our cosmos might be a three-dimensional membrane floating in a higher dimensional bulk where gravity can leak between realities. If true, dark flow might be the first tangible evidence we're not the only show in town. But there's an even wilder possibility. That dark flow reveals a cosmic structure from before the Big Bang. Some models propose that our universe inherited irregularities from a previous era, a cycle of cosmic contraction and rebirth. These primordial wrinkles, stretched to unimaginable scales during inflation, could still be tugging at matter today, like fossils embedded in the fabric of space-time. It's as if the universe has muscle memory, carrying the imprint of its birth pangs billions of years later. Then there's the higher dimensional angle. What if dark flow isn't about parallel universes at all, but about dimensions we can't perceive? Imagine ants crawling on a tablecloth. To them, the world is flat, until someone presses a finger down from above, warping the fabric in ways they can't comprehend. If our universe is that tablecloth, dark flow might be the fingerprint of something pressing in from a dimension we can't see. This isn't just theoretical gymnastics. Experiments like the Large Hadron Collider are already searching for extra dimensions by probing the behavior of particles at infinitesimal scales. Dark flow could be the cosmic scale counterpart to those efforts, hinting at structures too vast to see but too powerful to ignore. Of course, not all explanations require rewriting physics. Some researchers argue dark flow might trace back to an overlooked quirk of inflation, the universe's explosive early growth spurt. If inflation wasn't perfectly uniform, it could have left behind gravitational hills and valleys on scales larger than our observable universe. Galaxies sliding toward one of these valleys would look exactly like dark flow, no multiverse required. It's the cosmic equivalent of a tilted floor making marbles roll in the same direction, even if no one pushed them. What's fascinating is how these theories, no matter how speculative, force us to confront the limits of our imagination. Dark flow isn't just a puzzle to solve, it's a mirror reflecting how small our cosmic frame of reference might truly be. Whether it's evidence of a multiverse, higher dimensions, or primordial scars, one thing is clear: the universe is playing a game with rules we're only beginning to decode. And that's what makes this more than science. It's a reminder that the greatest discoveries often begin with a simple, unsettling question. What if we've been looking at the picture all wrong? Dark flow remains one of cosmology's great unanswered riddles, a cosmic whisper that defies explanation while daring us to look beyond the edges of our understanding. This isn't just another puzzle to solve. It's a paradigm-shifting enigma that forces us to confront the limits of our cosmic maps. Whether the strange motion of galaxy clusters is evidence of a hidden multiverse, a gap in Einstein's equations, or something beyond our current physics, one thing is certain: dark flow has already reshaped how we see the universe. It's a humbling reminder that for all our telescopes and supercomputers, the cosmos still holds cards it hasn't revealed. Think about what's at stake here. If dark flow is real, it doesn't just add a new chapter to astronomy, it tears up the old ones. For centuries, we've assumed the universe was uniform, self-contained, governed by laws we could uncover through observation. But if galaxies are being pulled by something outside that framework, it means our cosmic neighborhood might be just one room in an unimaginably vast mansion, with doors we haven't even found yet. The implications ripple far beyond academia. Philosophically, it challenges our place in existence. Technologically, it pushes us to build instruments capable of probing the unseeable. Culturally, it reignites that primal human drive to explore, to ask what else is out there. Yet dark flow's greatest gift might be its ambiguity. The fact that it hasn't been neatly explained, that it lingers in the realm of maybe, is what makes it so electrifying. Science thrives on these edge cases, the anomalies that don't fit. It's how we've made every major leap, from realizing Earth orbits the Sun to discovering space-time bends. Dark flow could be the next catalyst, the anomaly that forces us to rewrite the rules. Or it might fade into obscurity, a statistical quirk in the data. But even failure would be illuminating, because the pursuit of answers, not just the answers themselves, is what expands human knowledge. What comes next? Missions like Euclid and the Roman Space Telescope will sharpen our view, probing the cosmos with unprecedented precision. Supercomputers will simulate universes upon universes, testing wild theories against cold, hard math. And somewhere, a student staring at a star chart or a programmer sifting through data might stumble on the clue that cracks the case wide open. That's the beauty of mysteries like dark flow. They're not just for experts in ivory towers. They belong to anyone who's ever looked up and wondered why. So while we may not yet know what's pulling those galaxies, the search itself is a triumph. It proves the universe still has the power to astonish us, to remind us that curiosity is humanity's superpower. Whether the answer lies in parallel dimensions, primordial scars, or undiscovered physics, one truth remains: the cosmos is far stranger, far grander than we've dared to imagine. And that's why we'll keep searching, because the next great revelation isn't just lurking in the data. It's waiting in the questions we haven't even